Again, I'm Zafer Gedik from Sabancı University from Istanbul. In 15 minutes or so, I will try to finish my talk on basics of quantum computation or quantum computers physics part. I'm a physicist. Actually, I'm a theoretical physicist. And I was working on some problems on quantum mechanics itself, and all of a sudden, I ended up with some quantum algorithm and all these quantum business. I am now representative of Turkey in so-called quantum community network. From all countries in the Europe, we have one representative. Well, first, they talk about second quantum revolution. By the way, the colors are not accidental. You already heard about quantum manifesto. They borrowed these terms from some other terminology, but let's keep using them. Why do we have quantum revolution? Of course, if there is a second one, there should be the first one. The first one was almost a century ago. All these names here are very famous. Of course, you know Einstein, but there is also, you know, Heisenberg, Schrödinger, Dirac, and also, by the way, Planck. This constant, so-called Planck constant, is important because if you open a scientific paper, an article, whether it is about quantum mechanics or not, you decide if somewhere H is mentioned, Planck's constant is mentioned. So it is a sort of, you know, to solve this thing. Okay. Now, after this first revolution, new ideas, people spend a lot of time about the mathematics of quantum mechanics. You know, this is a typical, you know, old-fashioned board solution of hydrogen atom, energy levels, you know, magnetic moment, harmonic oscillator. These are all technical terms of, but they are all solutions of so-called Schrödinger's equation. This new physics. That was basic theoretical physics without maybe any expectation about applications, no technological revolutions. But now we are using them. These are just ones and zeros. You know, you can write any information using these two letters or numbers or any two choices. You can use two. When it is two, we call this as a bit in computer science. And bits are everywhere in classical systems. I even use this one. Maybe some of you use. And then diskettes, and then USB flash memories, CDs, everything. They all carry information. It doesn't matter where you write, but the information is the same. It is like, you know, copying a movie on USB or your cell phone. These are called bits. When it comes to quantum one, by the way, here we have quantum mechanics already. Because this instrument for us, cell phone or this other thing, they make use of transistors, right? Transistors are made of semiconductors, and semiconductors work on principles of quantum mechanics. But today, what we are talking about is not this indirect use of quantum mechanics. Directly quantum mechanical algorithms, processes we are talking about, and quantum computers are doing this. And it starts from the very, very beginning, from the bits. Bits are no more bits, but they are quantum bits. And we denote them most of the time by this notation due to the physics that you have seen in the previous picture in the middle, Dirac. So this is called as Dirac's notation, and it's actually called the cat, just a half of a bracket, the right hand side. And there are also brackets. And we have gates. By the way, anyone who still didn't see this gate, this is the gate, famous gate of Dolmabahce. This is the name of this room, and also there's Dolmabahce Palace. Gates change qubits. For instance, there is so-called an X gate or negation gate. When 0 enters to this gate, it becomes 1. Don't think this as a wire and then current running in time, but this is a sort of time image or word line, as they call it, special relativity. So time is running in this direction, and you have a qubit. Say, I am a qubit, I wait. Then I pass through X gate. So if I was 0, then I became 1, and otherwise, if I was 1, I would become 0. And similarly, we have Z gate. There is first strange thing is happening here. You see, there's a minus sign. What does it mean to have a minus bit? So you understand that there is something new. There are even some more weird things. We have so-called Hadamard gates. They can be neither 0 zero nor one. Such states are possible. If you ask what they are, it is very difficult to explain. As in this picture in Turkish, instead of ostrich, we say deve kuşu. Actually, it is just a combination of two words, camel and bird. So this is, in some sense, if you translate it, not as ostrich, it's actually camel bird. And sometimes some people do these jokes to some foreigners. You know, it is like ostrich. Neither camel nor bird, they just look in your face. But if you think in Turkish, it has a perfect meaning. So ostrich has nothing to do with camel and birds. It's something like that. So you take the 0 plus 1 divided by square root 2 for some reason, and it is both. Well, if you take this 0 and plus 0 plus 1 over the 2, instead of this, if we take two of them, for instance, 1 qubit here, 1 qubit here. Sometimes you can prepare states like this, 0, 0, or 1, 1. Never 0, 1, or never 1, 0. This is called as entanglement. Using entanglement, you can teleport, carry some information, quantum information from one point to another point. This is not beaming, by the way. Because if you look at these, science fiction movies, there you have a piece of matter, it disappears and it appears somewhere else. No, it is not this. It is just some way of carrying quantum information. I always like this analogy that maybe I can explain you. You have some quantum information, and you just take each piece of these Legos one by one and send or tell the information to your friend at some other point. Hey, Mike, I have now this little red piece. Okay, put it in position 3. Then it puts, etc. So at the end, your Lego, your shape is here because you use the same pieces exactly in the same way. But since you disassemble this one, it disappears. So you can never clone quantum information. This is the main difficulty. Because in classical circuits, we have amplifiers. There's a signal you can use, electronics for light, for electric signals to amplify it. We don't have this chance in quantum mechanics. There is a basic theorem. If cloning were possible, then you would travel in time, you would see the future, you would change the past. It would be very terrific for physics. So it is forbidden by their fundamental reason, so-called causality in physics. Well, let's come to computation, how we use them after this quantum business. I think I have used all of them. Even this one, my father had one in his bank office. But now, I can, okay. How to explain this in simplest possible way? There's a wording by Einstein, by the way, not simpler. It should have the necessary information in it to explain quantum computation and still simple. Well, I will talk about an algorithm, not because some people call it in this way with our name. In contrast, we call this quantum permutation algorithm, just because it is very simple and in fact simplest possible. We can prove that no quantum algorithm can be simpler than this. This is even simpler than so-called famous Lorentz algorithm. It works with a single Q-thread, and it has been tried in 2-3 years. It was published, and our original article was 2015 again. Now more than 10 experiments, nuclear magnetic resonance systems, superconducting systems, even this IBM quantum computer. Once you have a little 3-level system in your hand, you can try this algorithm because it is very simple. Even we are explaining this to high school students visiting our university. So let me tell you about this. And by the way, this was one of these experiments, and it is mentioned in National Science Foundation of Brazil. That was the news. Okay, here's the problem. This is real physics. I will now tell you a quantum computer, a quantum algorithm solution problem. So we start with, if you propose an algorithm, you should first put some computational task. That is, I will solve this problem, say factorization or even odd problem, something. Then you just put all possible classical algorithms, how to solve the problem classically. Then you say that, but in quantum case, using some quantum algorithm, I can solve this problem faster. Faster in the following sense, as the problem gets more and more complicated, while this, necessary instruments, gates or other things grow, here say exponentially, the one here say grows in a polynomial way, for example. Or in this problem, we will prove now that you can solve this problem in classical algorithms in 2 steps, but in quantum case, in 1 step you can solve. So the problem is the following. There is a black box, this blue anyway, and this is a permutation gate. That is, you have 3 objects, say 3 colors. Instead of saying numbers, I just chose 3 colors. It changes the color, or maybe leaves the color the same. For instance, red enters, say it becomes green. Blue becomes red, and green becomes blue. So we can summarize this if you want. This is just collection of the 3 slides that I have shown you. Put all these colors on a ring. It is something like rotation of this ring, okay? Because you see, blue becomes red, green becomes blue, red becomes green. This is a possibility. How many such operations do we have? I think almost everyone from finance know that that's a permutation problem. We have 3 elements, so we have 6 such things. Now let's run through these. For instance, this goes to this one, or this one, or this one, or this one. They add up to 6. But these 6 permutations can be classified into 2. One here, and a corresponding one. It's image in a mirror image. You see, mirror image just changes the chirality, right? It is something like this, and the other one is it's counterclockwise. So this is number 1. 1 plus 1, 2. 1 plus 1, 2. 1 plus 1, 2. So 6 permutations can be classified in 2 groups. Those in front of the mirror and those on the other side of the mirror. Here is the computational task or the question or the problem solved by this quantum permutation algorithm. Someone, say, nice to do it, anyway, brings a permutation box, and the question is, which one is it? Is it one from front of the mirror or other side of the mirror? We don't want which one it is, because we have 6 possible boxes. We don't want whether it is number 2 or number 5. We want just to know whether it is on this side or on this side. Technical term for this, those on this side are called as even permutations, those on this side are called as odd permutations. So, even or odd, how can we solve it? This is computational task. First, let's prove in 1 slide, we can solve this problem in 2 steps in classical physics, because, you see, if I check where green goes, you can say that blue. Okay? But if you look at a similar picture here, for instance, look at the 2 boxes explain this one. When you look at certain elements, say red goes where? Red goes, say, as a mapping, say, green. We have seen an example. But if you look at the position of red, we have 2 possibilities. For instance, here we have red and also red here. We have blue and a blue here. And say green and a green here. So you can never decide whether on this side of the mirror or on the other side of the mirror you are, or this box, by checking only one element. You need to check 2 elements, right? So it means that you need 2 computations. So to solve this problem, classically, we need to run, or we should put 1 bead or color ball into this box and see what comes out, and put the other one and comes out. And imagine, for instance, a science fiction case, say there's a box, you can use it only once. If you run this current through, it burns, for instance. you never have a chance for second trial, then you can never understand which one you have in classical way. But in quantum case, you can, because we have so-called superpositions, ostrich, deve kuşları. Because you can have 0 plus 1 divided by square root 2. You can have blue plus green plus red divided by square root 3, things like that. And if you do so, you can solve the problem. Here is the way. You can combine 3 colors. You can create such quantum superpositions. This is called as a, say left-handed, or it depends how you look at it, or right-handed combination. In technical terms, it's called as a Fourier transformation, actually. And this one is just the other way around, left-handed Fourier transformation, or opposite of Fourier transformation. One thing, maybe we should also mention this with my colleague Henry. Quantum computation is a green computation in the sense that things are reversible. So when you put, cow and obtain sausage here, you can put the sausage back and obtain the cow. This is not possible in classical physics, but in quantum it is. So if there's a gate which makes this balloon beat this combination, there is another gate which just does the opposite. In fact, you don't need any other gate. Just put on the other side, it comes out in the way that it was originally. So here is the processor. This quantum algorithm that I mentioned to you does the following. It just accepts this special combination and we look at the output. If it is the same, if this and this are the same, this is an even box. If this is switched to that one, it is an odd box. So simple. And the experiment of this algorithm was done before the original article was published. And this was done in a Q-treat. Instead of qubit, we have a three-dimensional system. It's called as quantum treat or Q-treat. And here they are. And this is, let me read it for you, what was it? Chloroform, deuterated. That is one of the hydrogens now deuterium, this one. And it's a chloroform. It is in liquid crystal form, and experiment is done. And a typical figure for this scientific experiment is this one. Look, you don't need to know what it is. You can read, I think, the words even and odd. This is number one. The other thing, these are some outputs. Even I don't know the details, but you see, when it is even, this is a tomography, astigmatic tomography. All are the same. But if it is odd, they are all the same, but this group and this group are different. So you can distinguish in single run. So simple. And we did the same experiment after 10 more experiments or so from our colleagues, ourselves as well. We connected to this IBM quantum computer. That time it was still small, it was 15 or so qubits. You can arrange it and you do some analog calculation, and you can solve the problem in this way. I hope that this was a simple enough experiment. This algorithm was not a very useful one. As I said, it is a sort of pedagogical one to understand why it works. 2 calculations for classical case, 1 single G is enough for quantum case. But you can solve some problems, more complicated problems. For instance, this one, factorization problem. How does it work? You can always multiply 2 numbers, but it is not an easy problem to check, to decide if a given number can be written as a product of 2 numbers. So this is one of the basic problems. And so-called Shor's algorithm can do this because quantum computers can perform so-called Fourier transformation, quantum Fourier transformation, much faster than classical. This is an interesting problem because in classical case, no one has proven that the problem can't be solved classically in a faster way. We don't have such a proof, but we don't have any algorithm, a classical algorithm that solves this factorization problem fast enough. In case of quantum, we have at least one. And the early version of this IBM quantum computer was used to show that 15 equals 5 times 3. Now, of course, we are solving many, many other problems. Okay, let's remember this quantum manifesto once more. It was almost 3 years ago. And if you look at the calendar, Eric already mentioned some details, but maybe we can just look at where we are now. So we can say that we are somewhere here. Are we successful? Let's come back to, for instance, this computers. We can, I think, safely say that in 4 years or so, we are at the point that they aimed. And the interesting part would be after 10 years. You see, general purpose quantum computers exceed computational power of classical computers. We are not yet at a stage where they are doing comparable things, but they are running. Now we have many quantum computers that we can connect and run some algorithm. And you can guess where they are from. The same year, this group, Chinese group, sent the first quantum satellite. What does it mean? It means that you have a satellite, and the satellite can communicate with some other points on the Earth, say at least, and you have a quantum channel, which means that a qubit here and a qubit here, they are entangled, or you can do quantum teleportation, things like that. And last but not the least, we should mention, you can connect to this RS quantum community network. This is now, I think, the most important initiation in Europe, quantum community network, and this is composed of some groups from each country, members and associated members of European Union, including Turkey. And we work on, several issues, including maybe convincing our governments for the importance of this new technology. This is a revolution. I should say that I have never seen in my life, and I said that my older colleagues say the same thing. Such an exciting period. We have several problems in our planet. Energy is one of them. We are looking for, fusion or other things. But quantum computers are in parallel. And if you think of examples, I learned a lot about finance applications today, but in other things as well, in science and in engineering. I think you, as experts or working in the field of finance, will appreciate this new kind of technology. So thank you. That's all, and maybe I can handle this slide for you. Okay, thank you.
So, just one question about the quantum communication. It's what the satellite from the Chinese is just communicating directly to parts of the nodes. Sometimes it's people talk about internet, quantum internet or so on, but that means just connecting different nodes. But this should be complicated. According to that, you cannot clone the.
Yeah, sure. We don't have cloning, but there are so-called quantum repeaters. You can guess the meaning quantum memory, and yes, we need to have certainly several copies at the beginning that we should have. But when it comes to the question is very important from quantum cryptography or quantum key distribution point of view, because if you send more qubits for the sake of stability of the system, then there will be some security issues. And quantum key distribution, I think we didn't mention it very much, but on the security side, on also finance side, I think it is one of the most important applications. Okay, thank you.